is specification verification for unrestricted algebraic effects and handling. Yahui is giving the talk?
Yes.
Yeah. Oh.
Is that?
Mm.
Okay. Oh, hi. Okay. My name is Yahui Song. I'm a research fellow from National University of Singapore. Today I'm going to present this paper on specifying and verifying the unrestricted behaviors of algebraic effects and handlers. This is a joint work with Darius. Darius is with us in this room, and also our PhD advisor, Prof. Wei-Ngan. Okay, so the user-defined effects and handlers getting popular because it provides a modular and a structured way for delimited continuation. And in languages like Okama or Coca, we program it using a way similar to the exceptions. So when we perform an effect in the middle, we pass the control to the handler as well as the current capture the continuation. So and then in the handler, you can resume back to this continuation if you want. So this flexibility allow us to do some creative things that you could can resume back to one part of the computation more than once. So that creates the challenge for verification tasks that if the continuation contains heap manipulating behaviors. So this brings out the motivation example. So in the middle of the computation that we perform an effect, and before that, we initialize the x with 0. After this effect performed, we increment the x value by 1 and asserting that x equals to 1. So far, we have no knowledge of what is the concrete handler look like, but the behavior fell into the following 3 possibilities. If we have a zero-shot handler, it will abandon the continuation completely so that there's no assertion reached at all. And if we have a one-shot handler that resumes back to the handler exactly once so that the assertion at line 8 should succeed. If we have a multi-shot handler, the assertion would fail specifically at the second time when you resume back to this handler to the continuation because x's value has been incremented twice. So the existing verification techniques for such programs fall into one of these 3 categories. Either it handles multi-shot continuation but with a pure setting, or it handles heap manipulating behaviors but have a restriction on one-shot continuation. Or it finally combines the multi-shot with the heap manipulating behaviors, but it have a restricted usage of the frame rule. So the understanding is that you cannot apply the frame rule if the contexts have unhandled effects. I'll add a little bit more explanation for the last 2 cases. So these 2 approaches are based on is achieved by a global specification in the form of protocol, capturing the interactions from the effects performed from the client, and also what are the possible reactions from the handler. So when we verify this code, when we reach this label, we go search from the global assumption protocols that and then retrieve the post condition that assumed that the handler would give us, and continue the reasoning onwards. So this is good because as long as every party follows the protocol's specification, then we can guarantee some safety properties afterwards. But the problem is such a design also poses these limitations here. For example, because it does not have, the handler will never have the direct access to the continuation, so that it have to pose this restriction that it has to be one-shot continuation. So the motivation becomes clearer that our work wants to target unrestricted behavior of the algebraic effects and handlers. We propose, I'll firstly show our specification language on the bottom here. So our goal is to achieve a fully modular per method basis verification that without any global assumptions on the behavior. So specifically, we capture the specification in the trace. We have a sequencing operator in the middle, and the atomic constructs includes the require, ensure. So these are similar to the assert, assume statements in some of the primitively supported languages, or the exhale or inhale in Viper. So the basic idea is require will consume some of the resources in the current state, and ensure will give back to the state. We also model unhandled effects and unknown high-order functions in a very similar way, that they are similar in the sense without the actual instantiation of the high-order function, or without the concrete handler implementation, the effects and high-order functions that they are essentially uninterpreted. So with that, we don't want to pose any assumption on that. We just leave it on the specification and carry it along. On this specification, we also support a try-catch logic construct. It looks a little bit heavy, but it's actually the key ingredients that we achieve this modular verification. I'll use an example to demonstrate that later. And then we have a set of normalization rules, because in the trace that you could have a set of require, ensure, ensure, require. And in that case, you could normalize into a single pair of require, ensures using bi-abduction. And the way how we handle recursively generated effects is via lemmas, and our verification tool can automatically prove lemmas as well. Okay, currently the logic we are built on top of that is actually separation logic. So this P and Q here is in the form of a sigma and the pi. So if sigma is the heap formulas and pi is the pure constraints. Okay, so let's come back to this motivation example, that how do we write specification for this code. So the specification of that has two portions separated by this label in the middle. So before this label, we ensure x now points to 0. Afterwards, because we have lost any information guarantees of x, so we have an existential variable z to denote the current value of x, and we ensure x points to z plus 1 by the end. Notice that this assertion has been propagated to the current state, current require via bi-abduction. So if you have a trace of require, ensure, require, it will propagate this require to the first require. Okay, examples of how do we do this when we have actual concrete handlers. So in the zero-shot handler does not care about this k and directly return, so that we ensure x value remains 0 and the return value is -1. If it's one-shot handler, we resume back with value 3, so that x is now indeed incremented to 1 and the return value is 3 plus 2 returned here. And when we have a multi-shot handler that you resume back more than once, as we discussed before, this will lead to assertion failure. So our specification for that is just require false. Sorry. The machine is tired. This is the connection. I feel like something is going on now. I have an adapter. Try this. Is it? That is a bit weird. But it's very small, right?
Because it's muted now.
It's getting something.
Yeah.
Thanks for waiting. Thank you very much. It could be a problem of my old laptop. Maybe I need to replace it. Okay. So the intuition, let's come back to. So we were talking about that we managed to handle different kind of handlers at zero shot, one shot, and multi-shot. So the intuition that we can handle such different unrestricted behaviors because we have the explicit access to the continuation. And this is passed to the handler. So you can just compose in a way whatever you like. So a little bit detail on the reduction rules. This is strictly following the semantics of the effect handling. So in the base case, also the purpose of reduction rule is from the left-hand side, all these rules starting from a try-catch construct, and the target is something without the try-catch. So the base case is if in the current try block there is no unhandled effects, we can just proceed to the normal handling case. And if it's the deep handler, and currently we are handling some effects in the middle, and we will continue to reduce the continuation first on the right-hand side and use this sharp in the middle, which means that whatever written continuation after the sharp is already handled by this current handler, so do not handle it again. And when we actually go to reduce this sharp operator, on the left-hand side, we will finally be able to replace all the occurrence of the K of handling the current effect with the current handled continuation. This is the key idea how we do this try-catch reduction. So I also want to explain that why we need this try-catch construct in the top level of the specification, because it looks heavy. But when we have unknown functions in the try-block computation that we don't know what's the behavior of f here, so we can't do the reduction. So I need to carry this try-catch along till the time that we have a concrete instantiation to this f, and then we can do a proper reduction to something without a try-catch. Okay, one example is how do we use lemmas. This example have a toes function which takes a value n, so that it recursively generates n flip effects. And by the end, we will conjunct all the flip. And then when the conjunction equals to true, we return 1. If it's false, we return 0. And the handler will resume back to this continuation with true and false respectively to backtrack the possibilities. And before you resume back, we keep a counter to remember how many times we have backtracked. And by summing them up, essentially to sum up how many backtrack branches that leads to all true. So it looks a bit complicated, but example is that when n equals to 1, the counter equals 2 because you backtrack twice, and the result equals to 1 because it's only one value equals to true. When n equals to 2, you backtrack first time, you have 2 incremented by 2, and for each of the cases, you backtrack again, so you get incremented 6, and the result is still 1. So we quickly find the pattern that the counter will be incremented to 2 to the power of n plus 1 minus 2, and the result value is always 1. Because there only exists one branch that with all the true flip results. So we prove this specification using lemmas. So this lemma says that on the left-hand side, there's a try-catch wrapped recursively defined toes function. On the right-hand side, we have an invariant. This invariant is to make sure that there's only one single required ensure. So regardless of all this recursively handling mechanism going on, we still can to prove that the final stage follows this specification. So we prove this specification here by applying the lemmas, and the lemmas can be automatically proved via the try-catch reduction and the unfolding rewriting defined for the entailment rules. Our implementation is built on top of OCaml, so we can take source code OCaml as the target program. We have a small benchmark. We mark the features, whether the proof is inductive, whether it had multi-shot continuation, whether the continuation is impure, whether it has a high-order functions in the middle. We also, with the flip example, we also show that how we write the lemmas for deep and shallow handlers and the right or left recursion. Last thing I want to note is that the lines of specification against lines of code, the ratio is less than 30% in this experiment. I would like to argue that the actual ratio can be even lower because essentially the only specification you need to provide is the lemma. The rest of the things that it can be reasoned pretty precisely following the execution semantics model. So the summary, when we say unrestricted handling, we actually mean is 0, 1 multi-shot, and the continuation can be impure, different kind of handlers, left-right recursion. And the rest of the things are the ingredients that we have in this paper. The takeaways I want to emphasize after the talk is that let's do not assume. I know many of the mechanisms are built on top of this assumption and do an early reduction. But to achieve a more precise verification seems that we should not assume for both high-order functions and the effects. And we achieved the modular specification without any global assumptions by these try-catch constructs. The intuition is that you should allow the handler to have explicit access to the continuation and can be composed as needed. With that, I need to advertise that I am looking for a job. So in case you are interested in my work and talk, I'll be happy to talk with you. Yeah. Thank you very much. I'm happy to take questions.
Hi, I'm
Yes.
Cesar Andrich from MPISP.
Hi.
So in your post-condition, you talk about references, and the references in OCaml have this monotonic property that they cannot be freed. So you have something to talk about. Did you try to write some other kinds of invariants?
In the post-conditions,
in the post-condition.
we're trying to guarantee that the counter's value, has been incremented to some, so it starts with the value W, and it will be incremented by 2 to the power of n plus 1 minus 2.
Yeah, but from how I understand it is, you can write a post-condition about the counter because the counter cannot be freed.
Oh, yes.
There are many things that, like, many properties that just disappear after you call an effect.
Right.
Did you try some other things, or do you have any insights?
I think in this paper we don't talk about that, and also in the target language we don't have a free operation, so it cannot be freed in our current target language. Of course that can happen, but perhaps we just need to add into the free operation and then consider the post condition of free operations.
Okay, thank you.
Thank you very much.
Hi, Sam Lindley.
Hi.
University of Edinburgh.
Yes.
You said you did multi-shot, but OCaml by default only has single shot.
There are libraries.
You used, okay, well,
Yes.
Daniel Hillstrom's library did you use? Or?
Right.
Right, okay.
Yeah. But I think the multi-shot is not, I think there's a whole discussion of whether we need to use, it's a little bit hard for me to convince why multi-shot continuation is useful as well. Indeed, but we work around that with the libraries that they provide. It's still working fine with our examples.
Okay, and another quick question. Have you considered trying this with other systems that more
yes, I read
actively
your paper.
support multi-shot?
Sorry, can you say that?
With other systems that are designed to support multi-shot from the beginning?
Without the design, without the...
Like, I don't know, Coca or other languages?
Other languages, of course, yes. We are looking for applications for this system. One direction is we are trying to verify reset shift programs, which are more fundamental constructs for controls. We also look at your paper on WebAssembly that is supporting these effects handlers.
Single shot.
Oh, single shot, okay, good to know, yeah. I think personally I will be like to verify such programs, yeah.
Thanks.
Thank you very much. Thank you.